how we get moment generating functions of sums of independent variables. Pardon me. So we did that. I think that was the last one we talked about last time. Let's look at this next one here. The idea behind this one, we've done things like this before. But this one with the Poisson, this is a good review for things that we talked about earlier in the semester. So we've got accidents in a given week is Poissonly distributed. Poissonly distributed. Sounds like weird. Has a Poisson distribution of a mean of 2. And we're assuming that week to week the accidents are independent. What's the probability of exactly 7 accidents in a 3-week time span? So what we can think of, and the whole idea behind this is we've already done this earlier in the semester, but the idea is that we can think of this as a sum of independent distributions at this point. We can think of x1 being what happens in the first week, x2 being what happens in the second week, x3 was what happens in the third week, and add them together to get the total number of accidents, right? And then the idea behind this is that we talked about last time, if you do a sum of independent Poissons, what type of distribution do you get? A Poisson again, right? And what do you do with the parameters? Add them, right? And in this case, the parameters are all the same. They have mean 2. So if we want a 3-week time span, then what's our new parameter? 6. There we go. Yeah, your lambda would be 6 in this case, right? Because it would be 2 plus 2 plus 2, since we would just add them all together. So then the probability that you would have exactly 7 accidents in 3 weeks, remembering what our Poisson PDF looks like. Okay. Yeah, I needed 6 p's there, right? Good. Yeah, it's lambda to the x, e to the minus lambda over x factorial. Well, whatever that turns out to be. Again, that was the idea. We did things like this earlier in the semester too, right? But we're just re-verifying this again through the language of looking at the moment generating functions and seeing what happens when you add those distributions together. All right. Again, the idea behind that is that when you add up Poissons, you get a Poisson. Okay, so same idea here, except that rather than just adding them, we're taking the mean. So we're taking a random sample of size n, and we're going to come back to this idea as we go along. Taking a random sample of size n, and in this case, looking at how the mean of those things is distributed. Well, how do you calculate a mean? What do you do? Just in general, if you have n things, how do you take a mean? Yeah, how many there are, right? So in this case, if your x1, x2 out to xn is a random sample, so again, that means that all of your x sub i's there are independent, and they're all coming from the same distribution. When we say random sample, that's what we're assuming, right? They were all independently selected, so we can think of them as independent random variables. And they're all coming from the same underlying distribution. Pardon me. Then x bar is going to be your, I'll write it as a sum here, of I equals 1 to n of 1 over n times x sub I, right? Now, what did we do here? We've added up a constant multiple, because the n's not changing, right? We've added up a constant multiple of a sum of independent random variables, right? They're all independent. We've got a constant multiple of each of those variables, right? So
What's its moment generating function going to look like? Well, again, when you add independent random variables, what do you do with the moment generating functions? You multiply them together, right? When you have a constant times the random variable, how does that constant play in? What do you do? It's not quite taking it outside, right? For a moment generating function, what happens with it? Yeah, it multiplies by the t, right? So I would do the product. So when we have a capital pi, we have a capital sigma to do sum. A capital pi with indexes also tells you to do a product. It's like a sum, okay? In case you hadn't seen the notation before. You'll take your moment generating function of each of your x sub i's. I'll write it as an I here, but we know in this case they're all independently generated. And then you would put in 1 over n times t for the t. So it'd be t over n in there. This is just using the stuff we've already talked about, right? When you add up the random variables, you multiply, when you add up independent random variables, you multiply the moment generating functions. And when you do a constant times a random variable, you replace the t with the constant times t. In this case, your constant is 1 over n.
Okay, so where'd the 1 over n come
from? Add them up and divide by n. We're doing the mean.
Oh, okay.
And I just put it on each term rather than taking it over the whole sum. Yeah. Yeah, usually you would think about it that way, right? So I just put it with each individual term. Yeah. And the reason why is so I can do this. Yeah. Say it again. So if x has moment generating function m sub x of t, then y equaling a constant times x has moment generating function that. I take out the t and plug it with a constant times t. That's in general. All right, so let's go back over to what we have here. They tell you in the problem, well, basically they remind you what the moment generating function is for a Poisson distribution. And so now they say, what's the distribution of a mean of a random sample from the Poisson distribution? Well, using this, we would do the product of the moment generating functions and replacing the t with t over n. It's the same distribution every single time, right? So we're going to have something raised to the nth power because it's the same moment generating function multiplied by itself n times. What are we going to plug in there? We're going to take e to the lambda times e to the t over n minus 1. Right? We agree with that? Now remember, we've got, this is, pardon me, one exponent raised to another. Shoot, pardon me, I'm sorry. As one exponent raised to another, so you would multiply your exponent. So all I would have here is e to the n lambda times e to the t over n minus 1, right? That's not quite a Poisson moment generating function, is it? What's off about it is that part right there. We agree? So notice that the mean itself does not have a Poisson distribution because I don't have the right t value here, right? Remember, it has to be constant times e to the t minus 1. I'm not allowed to have a change in there, right? It has to be the same t. So going back over here then, oops, didn't change it back to my pen. Looking back over here, well, sorry, let's look up here. Notice that knocks out these three choices, doesn't it? Because I know right away that x bar itself, the mean of the x's, does not have a Poisson distribution, okay? Because it doesn't have the right exponent, right? Okay. So it must be one of these other two. So if I go back to just n times x bar, looking at that, that's just the sum of your x of i's, isn't it? And we know that a sum of x of i's, we know that a sum of Poissons is Poisson, right? So this is a Poisson. Because notice in that case, you're not replacing this with a t over n anymore, are you? Okay. What do you do with the parameters in that case? For Poisson, what do you do with the parameters? Add them. So we get a parameter of n lambda in that case. And notice we could actually verify that with what we just came up with in another way. This, what we came up with, is the moment generating function for the mean. Sorry, that was in my hair. This is the moment generating function for the mean, right? Okay. Now we have a constant times that random variable. We know how to do the moment generating function for a constant times a random variable. You replace the t with that constant times t, and then your n's cancel. And I see that n lambda here as my parameter then. Okay. So to get that n to cancel in the denominator, I would need to put an nt in the numerator, right? So that's why I have the n times the random variable there. So as the mean isn't quite Poissonly distributed, I know it's a weird word, it doesn't have a Poisson distribution, but a constant times it does. And we're going to use that kind of concept, here in a little bit, but you also use it a lot in statistics to do a constant times a random variable to give a distribution that you want. Any questions yet? Well, I just told you what the answer was. It was this one. So which letter is it? It's E, yeah. Okay. All right. All right, let's look at the next one. Pardon me. This one actually tells you what you're supposed to come up with. You have a bunch of exponential distributions added together. And it says, show that you have a gamma. So this is telling you that a sum of independent and identically distributed exponentials is a gamma distribution. Okay. So let's see why. What is your moment generating function for each of your random variables, x sub I, each of the exponential ones? What is a moment generating function for an exponential distribution? You're thinking of the CDF. Yeah. Yeah, it's 1 over 1 minus theta t. Good. Okay. So using what we just talked about a minute ago, if I want the moment generating function for W, which is what they labeled the sum here, when we add random variables, what do we do with the moment generating functions? Multiply. They're all identical here, so we're going to multiply each of them together. So I would have 1 over 1 minus theta t to the h, and I could just move the h down to the denominator. And what is that the moment generating function for? Gamma. Oops. Remember whatever the alpha value is goes first, and then yeah. whatever the alpha value goes first and the theta value goes second. So there's your theta, there's your alpha. And the mean of a gamma distribution is what? What is the mean of a gamma distribution? Yeah, alpha times theta. In this case, your alpha is h, so that you really do get h times theta. They just changed the name of it on you. The idea here is that, again, a sum of independent exponentials is a gamma. Independent and identically distributed exponentials is a gamma. Yeah. All right. This one basically is asking you, what is the distribution of a sum of independent and identically distributed gammas? Any guesses? What it might be? Probably a gamma again, right? What parameter is going to change? Is the theta going to change or is the alpha going to change? The alpha is going to change, right? Because again, your moment generating function for each of your x's here is going to be 1 over 1 minus 5t to the 7th, because alpha is 5 and, sorry, try that again. Alpha is 7 and theta is 5. When I multiply these together, does the 5 change? No. We're just going to take 1 over 1 minus 5t to the 7th and then cube it, right? Because I got 3 of them in this case. So you get 1 over 1 minus 5t to the 21st. Still gamma. Still the same theta, but the alpha now has tripled. And that's the only thing that's going to change. Instead, if you do n of these, you'll still have the same theta, but your alpha then becomes n times alpha. Does that make sense? So independent and identically distributed gammas together also make a gamma. Notice in this case, what if we did the mean? Just to do this in general. Let's say we had each x of I is gamma of alpha theta. Let's look at the moment generating function for the mean. Now remember, for gammas, your moment generating function is 1 over 1 minus theta t to the alpha, right? If they're all identically distributed, I'm going to multiply all of those together, right? So I'd have 1 over 1 minus theta times something to the alpha to the n, that way, right? Now, I didn't fill in the t because why? I'm looking at the mean. What do I have to replace the t with? T over n? So now we get 1 over 1 minus theta over theta over nt to the n alpha. Now before, when we did Poisson's, we said that the mean wasn't Poisson, but a multiple of the mean was Poisson, right? Is that gamma? Yeah, that is a gamma, right? The theta has changed, but it's still a gamma distribution, right? So this is gamma. What's your new alpha? N alpha, and your new theta is theta over n. Good. Exactly. So this one tells us that a mean of gammas is still gamma. Also would tell you that a mean of exponentials is also a gamma. Because your alpha starts off as 1, right, for an exponential. That exponential is a special case of the gamma, right? Questions on that one at all? This is why, by the way, this is why we play around with these moment generating functions, is to help us recognize new distributions from random samples. It's one of the reasons why we do it. All right. We should be able to do this one pretty straightforwardly. We've done one like this already. Looking at your moment generating functions, what type of distribution do X and Y both have? They're both normal, right? Those are both normal distributions. Okay. This one says we're going to add X and 2Y. Well, since we're adding, what will we do with the moment generating functions? Multiply, and since we have a 2 in front of the Y, what do we do with that? Yeah, replace the t with 2t for the y, all right? So if I'm going to just call this w so I can use the subscript. We would have e to the t squared plus 2t, that's the moment generating function for x, times e to the 3 times 2t squared plus 2t, right? So, pardon me. And what do we get? E to the, that's 12t squared plus another t squared gives me 13t squared, and then plus a 4t. So it must be letter E there. I think we did this one. This feels familiar. I must have copied this one here twice. That feels very familiar from what we did last time.
There was something with the 13.
Yeah. But the 13 was right because my brain was not working right that day. Okay. All right, but still here, it's the same idea. And what's important with this one in particular is that when you add independent normals, you still get a normal distribution. Okay. What did we do with the means? We just ended up adding them together, right? Add the means and add the variances of the variables. Okay. And that's true in general. We'll come back to that here in a little bit. All right, let's do the next one. Just reinforcing different things here. This one's got a little bit of an extra piece in here. So let's talk about what happens there. Notice that this one's a shift. Before we start anything else, what type of distribution does X have? It's gamma, right? The alpha is 3, and the theta is 0.1. Good. Great. Recognizing those things. Cool. So that's definitely a gamma. This was just asking us what's going on with the moment generating function of this new thing. Now, we have talked about this with variances. Let's talk about variances just for a second. If I were looking for the variance of y, what does the 3 do to the variance? Yeah, it's squared, right? So you'll multiply by 9, right? What does the plus 5 do to the variance? Nothing, because remember, again, a shift does nothing to the variance, right? Okay. Just wanted to kind of try to review as we go along as well, right? Okay. All right, so let's talk about moment generating function. Let's just do it from the definition. By the way, what would we anticipate we're going to do with this 3? In terms of the moment generating function, what do we anticipate is going to happen? Multiply by the t, right? Okay. So we're going to probably replace the t with a 3t, right? But let's see what happens with that plus 5 as we go along. So remember, by definition, the moment generating function is the expected value of e to the t times the random variable, right? And in this case, pardon me, your random variable is 3x plus 5, right? All right, so distributing the t and then breaking up that sum in the exponent as a product, I write this as e to the 5t times e to the 3t times an x, right? Now, not worrying about what the function is on the inside of the parentheses, by definition, expected value is sum or integrate, depending if it's discrete or continuous, of the function times the PDF, right? But when we're doing that integral or sum, what values are we interested in? T's or X's? X's, right? So as far as the X is concerned, the T is a constant. So what can I do with that e to the 5t? Bring it out in front of the expected value, right? As far as the expectation goes, the e to the 5t is a constant, right? So I pull it out in front. And I have expected value of e to the 3t times x. And now this is just the moment generating function for x with t replaced with 3t, isn't it? Okay. So you have e to the 5t times 1 over 1 minus 0.1 times 3t cubed. I mentioned this a while ago. I'll mention it again here. Moment generating functions are closely related to Laplace transforms in differential equations. Right? You do Laplace transforms, you do the e to the st times f of t dt. Right? For those of you who've had DiviQ, right? That's what the Laplace transforms look like, right? When you had a shift for your function, what pops up in the Laplace transform? An e to a power. Right? When you have a shift, again, if you ever had DiviQ, you can ignore what I'm saying right now, right? But when you have a shift in your function, whatever you're doing with the Laplace transform, an e to that shift times t popped out, didn't it? It's been a while since I've taught differential equations, but I remember that stuff, right? Well, Laplace transforms are one of the big ones that you do in DiffyQ. Okay, so again, it's not a huge surprise if you've had differential equations that you've got this extra piece that pops out. They're related to the Laplace transforms. Again, if you haven't had Laplace transforms, then just believe it. Okay, but generally speaking, now when you've got this shift piece right here, what's going to happen in your moment generating function is you're going to get an e to that shift times t that you're going to multiply. Okay, that happens in general. So if just y is x plus some constant, I'll call it a, then the moment generating function for y is e to the at times moment generating function for x. That happens in general. Okay. I always say when you're learning math, you have to be very zen about it because everything's connected. Okay. Yes. Yeah, the 5 is just a constant. Yeah, so say it again. It does nothing to the variance. It does something to the moment generating function. It'll also do something to the mean. The plus 5 doesn't do anything to the variance because a shift doesn't change how much it's spread out by. But it does change where the location of your distribution is. This okay? All right. Let's see. This is similar. I'm going to skip this one. But to mention real quick, what kind of distribution does that have? Gamma. So when you add it, it's also still going to be gamma, right? So you should be able to figure out what the variance is and then take the square root. Because remember, a variance for gamma is an alpha theta squared, right? Okay. And then remember, again, you don't change your theta, but it changes the alpha. Okay. So just to remind. What's next? This is a nice little review for just what moment generating functions give you. They tell you that the functions, don't worry about the context. You've got 3 random variables and they tell you they're mutually independent. So if you want the combined losses or the sum of those 3 random variables, what do you do to the moment generating functions to get the moment generating function of the sum? Multiply them, right? So your moment generating function for x here will be the product of these pardon me. 1 minus 2t to the negative 10. If I added correctly. Feels like I added correctly. All right. So we found the moment generating function. How do I use the moment generating function to find the expected value of x cubed? What do we do? Yeah, take the derivative 3 times and then plug in 0. Good. Yeah. Remember, we take the expected value of x cubed will be the 3rd derivative of the moment generating function plugged in at 0. One of the reasons why I wanted to talk about it, because it reviews that little concept. We're getting close to the final, right? So I'll try to review as we go along. Okay. So 3rd derivative. Well, that looks like fun. Well, if I do the 1st derivative, we'll bring a negative 10 down. 2nd derivative will be a negative 11 down, right? Because I have to subtract 1 from the exponent. 3rd derivative, I'll get a negative 12 down. So I'm going to end up with a 10 times an 11 times a 12. Now, why did I get rid of the negatives? Well, also, each time I take a derivative, what's going to pop out with a chain rule? Negative 2, right? So I'll have 3 2's that also pop out, right? Because I'll have a 2 each time. And then 1 minus 2t to the negative 13th. That part doesn't really matter because when you plug in 0, I just get 10 times 11 times 12 times 2 times 2 times 2. This looks like a fun calculator problem. Whatever 1320 times 8 is. 12 times 11 is 132, so I got 1320 and then times an 8. That okay? All right. Now, let's go back and look at these moment generating functions. What are these? What type of distribution are these the moment generating functions for? It's specifically what specific, it's a chi-squared, isn't it? Yeah. It's a chi-squared distribution, isn't it? Because the theta is 2. What's the degrees of freedom in each of them? How do you figure out the degrees of freedom? The exponent is what? It's r over 2, right? So the first one has 6 degrees of freedom, the next one has 5, the next one has 9, right? When we add independent chi-squareds, what do we end up with? A chi-squared, and what did you do with the degrees of freedom? Add them, yeah, okay? So, again, independent chi-squareds is still chi-squared, and you add the degrees of freedom, okay? So I'll write that off to the side here. If x sub I is chi-squared of r sub I, then the sum of the x sub i's is still a chi-squared of the sum of the r sub i's. They have to be independent. That's important. Okay. All right. In particular, what special distribution did we say when we squared it became a chi-squared? Special distribution that you have a nice table for to calculate probabilities. The standard normal distribution, right? So in particular, if z is normal is 0, 1, then the sum from I equals 1 to, I'll call it little n, of z squared is chi-squared of n. Because when you square a standard normal, you get chi-squared of 1. So we're just adding a bunch of chi-squareds of 1s together. Okay. Why might this be important? Well, if I square a standard normal, I might be looking for variance types of things. So this talks a little bit about the distribution of the variance, of how a variance is distributed. Okay. This is important. So if you've done any statistics at all that talks about analysis of variance, you've used the chi-squared distribution before. And if you haven't done that and plan on taking a statistics at some point, you will use a chi-squared distribution for that. All right. So lots of things that we've learned about in this section, right? And again, like I told you last time, I did post right before class. There's a nice little practice quiz in there. It says it's worth 10 points. That's not a real quiz. It's just in there, right? So not worry about the grade. And you can repeat it as many times as you want. But it just has 10 questions in there of just asking you, if you've got this scenario, what kind of distribution does this thing have? Okay. So it's just a matter of just kind of playing around with it. You can go into it as many times as you like, although it's not randomized. So it's just the same questions over and over again. So I don't know how many times you'll want to do it before you're super bored about it. But it's there if you want it. All right. So, in any event, what we're going to be concentrating on basically for the rest of the semester, and I know we have a test in between, so basically the rest of today and Thursday, what we're concentrating on is what happens when you have independent normal distributions, okay? And then what happens if you've got distributions that aren't normal, but you have a random sample that keeps getting larger and larger and larger. Okay. So that's kind of the idea behind what's going to go on for the rest of what we're going to talk about. So we already mentioned this before, but let's look at this first problem. It's got a lot of things going on here. So it's got hardness measurements from a couple of furnaces. And it's telling you what the distributions are for the hardness levels of the two different furnaces. I know, lots of setup into this problem to get to an easy particular part. I'm not going to worry about sketching the PDFs because the normal PDF, I'm not too worried about getting a sketch. But if you really were sketching it, just a sketch and not really trying to put it on a actual graph idea, I'd have one of these has a mean of 47.88, and it's going to be a bell-shaped curve like that, right? The other one, the mean is going to be over to the left, so the top of my hill is going to be farther to the left, but my bell is going to be more spread out because the variance is bigger, right? Something like that. That would be a rough idea, right? I know one is skinnier than the other, and one is to the left of the other, right? Okay. All right. So basically, what they're trying to compute is if I have an observation, I want the observation of
my x1 to be bigger than my observation of the x2. So just from a graphical perspective, probably going to be pretty large, just the way it's looking at it, right? Relatively speaking. And we would assume it's going to be bigger than a half because my mean is bigger than a half here. Or my mean of my first one's bigger than the second. That's not really the point of this problem. Okay. The point of the problem is this next part. We want the probability that the hardness level from the first furnace is greater than the hardness level from the second. That's what it's asking about, right? So the first thing I would do is subtract this and put a 0 on the other side. Now, why would I do that? What are we assuming about x1 and x2? They're independent and they're normal, right? Sums and differences of normal distributions are normal, right? So this is going to be normal. What do you do with the means? You're going to subtract them in this case. So we'd have 47.88 minus the, 43.04, right? We're going to subtract them. But what do you do with the variances? Well, just the variances for the distributions. What do you do? We're going to add them, aren't we? Right? Because you would, if you think about that as a constant of a -1, you'd square it, right? So we'll end up adding the variances. So 2.19 plus 14.89. Now I have the mean and I have the variance of a single normal random variable. Do you know how to solve this problem now? Yeah, take a z-score, right? Right. So what do we get? Well, first I've got a greater than problem, so I would do 1 minus that, right? Agreed? And then I would have 0 minus 47.88 minus 43.04 is what? 4.84? That is 17.08. So I'd have to do the square root of 17.08 because we have to divide by the standard deviation. Make a z-score, right? Isn't that what we would do? Yep. Okay. So the 4.84 here is just the difference of your means, assuming I did my arithmetic right. The 17.808 is the sum of your variances. We just converted it to a regular old normal distribution problem. Okay. So the idea here is that, just write this off to the side again. If x sub I is normal on mu sub I sigma squared sub I, then the sum, and they're independent, then if I do the sum of the x sub i's from 1 to n, this is still normal. We add the means. Oh, so I should say a sub I, constant times that. We would add the a sub I times mu sub I. And we also add the variances, except that I got to square each of the constants. And that's in general. If you've got independent random normal, independent normal distributions, sorry. If you have independent normal distributions, the sum of them is still normal. The difference of them is still normal. Any linear combination of them is still normal. Sums and constant multiples.
It's true in general. But again, like I said, this is the whole point of this entire chapter is what's going on with these things. All right. What about the mean? What if I do it this way? What if I do the mean of the observations? And let's assume that each x of I is the same distribution, just to make our lives easier. Well, looking at this formula, what do we end up with? We would have this, the mean of the y would be the sum from I equals 1 to n of 1 over n times the mu, right? Because each one has the same mean. What does that add up to? Just mu, right? It's n times, because notice there's no i's, right? I add up the same constant to itself n times. What about the variance? Well, same idea. But in this case, I'd have 1 over n squared times sigma squared. What do you end up with this case? Yeah. Well, how many times are you adding this to itself? So what's n times 1 over n? Right? The n's will cancel. Yep. What do you get in the next one? Sigma squared over n. So notice that and this is a very, very important statistical concept, by the way. And this pops up a lot. When you do a random sample, and do another 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 random sample, and look at what the mean of those random samples are over and over again, the mean of those means is the same as the mean of the underlying distribution. It doesn't change. Okay? But what just happens to the spread as you take more and more samples? It's smaller and smaller, right? So as you take random samples, things start to gather around the mean. So what that means is that if you get something where you've taken a random sample and it's way far away from what you would expect the mean to be, you think that something's wrong, right? Because if you do random samples and take the averages, you don't expect a lot of spread. So if you've ever seen the movie Stand and Deliver, it's about a teacher that goes into inner city Los Angeles and teaches AP calculus to a bunch of kids who haven't had a lot of math background in the past. Teaches them a lot of different things, and they all score really, really well on the AP exam. Except that was out of line with what they've done in the past and out of line with other similar schools. So the College Board thought they cheated. And they invalidated all the scores. And they had to fight, and they had to retake the test, and the test came back and they still did well, and so they restated the scores. But that was a statistics thing. The mean of their scores was so far out of line with what would be expected from a mean from a school similar to it that the College Board assumed they cheated because the probability was so low that they would be able to do that. So this happens in statistics, this idea that as you take random samples, the spread goes down, helps you identify if something weird's going on. Gives you some cases where some evidence that something might be going strangely. Okay, and if you've done any statistics, and I know I've said that millions of times, it feels like this semester, you've done hypothesis testing where you reject null hypotheses. That's the idea that you're doing. You're saying that the probability that you had a random sample that gave you that value is unlikely to have happened based on the assumption you made. So you assume that your assumption was not right to start with. So this is where this stuff is going. And we're not going to get to that this semester because that's the next semester. Okay, but that's why we're studying these things. All right. Okay, let's go on to the next one here. See what we got.
Will this stuff be on the exam Tuesday?
This stuff will not be on the exam Tuesday. But the ideas of doing the sums of the distributions will be. Yeah, this will be on the final though. Okay, yeah. Okay. And I'll get a review sheet posted this afternoon so you can see what kind of problems are on there. Okay. All right. So let's look at this one. We've got a random variable that's normally distributed with a mean of 6.05 and a variance of 4/10,000ths. Now, part A should look like something that's on this exam coming up because part A is just what? Yeah, it's just a normal distribution problem, right? Subtract the mean, divide by the standard deviation, get the z-score, right? Use your table, right? That part A is something that we've already done, right? Right? So for part A, it's already set up as a less than problem. So you would have you do 6.0171 minus 6.05 over square root of 0.0004. And go about what we've done before, right? It's already set up as a less than problem. Subtract the mean, divide by your standard deviation. Look it up in the table or use your calculator, either or, right? That's not anything new, is it? Okay, I agree. That one's not new. Pardon me. I'm not going to do the next problem just because it is a nice review. What kind of a problem is part B? You're going to select 9 boxes at random, and you want the probability that at most 2 weigh less than that value you just found, or that you're considering in part B. What kind of problem is that one? What kind of distribution are you talking about there? It's close to the hypergeometric because let's assume we have an infinite number of boxes. So they're all going to have the same probability of weighing less than that value. You're choosing 9. You're counting how many have less than that value. Let's say binomial, right? It's a binomial distribution. Your P for part B is going to be this value that you find in part A. Okay. So this value here is your P from this is your P for part B. Oops. So in part B then, we want at most 2, right? So you would have none, which would be 1 minus P to the 9th, right? That would be none of them, wouldn't it? Plus 9P times 1 minus P to the 8th. That would be exactly one of them. And the next one would be 9 choose 2 P squared times 1 minus P to the 7th. All right, this is y equal to 0. This is y equal to 1. That is an ugly looking y. This is y equals 2. All right, remember doing those binomial problems? I didn't actually calculate what the p was to put in there, but that's how you do it, right? I didn't write out the coefficients in there, but that's 9 choose 0 times p to the 0. 9 choose 1, and then p to the first, and 9 choose 2 p squared. All right. Part C is actually the new one, the new part. Pardon me, goodness gracious. Sorry. Part C is actually the new part. We're doing the mean of 9 boxes, and it asks you what's the probability that the mean is less than 6.035. What I know it's normal because we just said the mean of independent normals is normal, right? What's the mean of the means? It's just the mean, right? Which is 6.05 in this case, right? What's the variance of the means? Yeah, this variance over n, which is 9 in this case, right? And now it's a normal distribution problem, right? At this point, it's literally the same things you've done before. Okay, so your probability that x bar will be less than or equal to 6.035 will be 6.035 minus 6.05 divided by the square root of that new variance. You can do phi of that, right? The CDF. It's already written as a less than or equal to problem. Basically, like I'm talking about, these two sections, 5.5 and 5.6, are really trying to go about and say, we're going to convert new problems into old ones, right? This is stuff we've already done before with finding the normal distribution problems, right? So all we're doing is just converting what we're being asked to a normal distribution problem. Questions on that one? All right, do another one. This one looks just a bit strange. All right. So we know that the square of a standard normal gives you what type of distribution? Chi-squared on 1 degree of freedom, right? So let's look at this first part, where they ask you the probability that 796.2 is less than or equal to the sum from I equals 1 to 16 of x sub I minus 50 squared is less than or equal to 2630. Okay, so there's a lot of things in there. Let's just concentrate on this part right here. What's been subtracted off relative to the type of distribution that we have? What's been subtracted off each x sub I? The mean, right? And that's the first part that we do to compute a z-score, right? What's missing from computing the z-score? What's missing? Divided by the standard deviation, right? So what do you think we need to do to everything in this double inequality to convert the inside piece to a square of a standard normal? What do you think we should do? Divide by, close. I need to divide the inside by 10. Yeah, right? So I'm going to divide everything by 100, right? Yeah, so I'll need to divide everything here by 100 so I can pull a 10 on the inside. You were exactly right about the 10. Okay. $26.30. That's 26.3. There we go. So now this part right here, so I'll circle it in red. What type of distribution does that have? And how many degrees of freedom? That part has 1. How many of the ones are we adding together? 16. So the degrees of freedom is 16. Yeah, exactly. Good. So the degrees of freedom here is 16. So now if you wanted to find this answer, we would need to go to our chi-squared distribution table or use Excel or use a calculator. I think I have chi-squared saved in here. I do. Here is 16 degrees of freedom. Here's your 26.3 right here. Here's the 7.962 right here. All right. Going back up to the top, then, what would we need to do to find the probability between them? Yeah, subtract those two values, right? Remember doing those? I mean, it's been a little bit, but remember doing those? Find the values in the table and go back up to find the corresponding probabilities, right? So going back over here then to where we were, this will be 0.95 minus 0.05, which will give us 0.9. Yes? Because I have to pull a 10 inside the square. I have to have a square of a standard normal, right? Inside the squaring has to be x minus mean over standard deviation, right? So I can't divide by 10, otherwise I'd have to pull in the square root of 10. I've got to divide by 100 so that I can pull in a 10 on the inside, right? I have to be able to pull the square out. That's why I have to divide everything by 100 and not 10. All right. What's different about part A to part B? And this is, again, important for statistics. I keep saying that, but it's important for statistics. Okay. What's different about part A to part B? It's not a trick question. What's different from part A to part B? Besides the values on the outside. Don't worry about I'm not worried about what the numbers on the outside of the inequalities. I've replaced with the known mean of the distribution, right? Notice the original thing says I'm assuming that the mean of the distribution is 50, right? If you're taking random samples from some unknown distribution, do you think you know what the mean is to start with? No, okay? So when you're doing statistics, you're going to estimate the mean of the distribution. What do you think your best guess for the mean of the distribution is if you have a random sample? What do you think your best possible guess is to do that? Yeah, take the mean. Well, you take the mean of your random sample that you have, right? That's going to be your best guess as the mean of the distribution is to take the mean of the random sample you have. So rather than having this 50, you might be interested in probabilities using your estimate, right? Okay? That's part of what statistics is. It's called inferential statistics. You're trying to make inferences about a population based on a sample, right? So you have to try to make guesses about what's going on based on limited information and trying to calculate the probability that you might be right. That's what statistics is about, okay? All right, so what happens is when you make a guess, and in particular what we're doing is we're estimating a parameter, we end up losing what's referred to as a degree of freedom, and that's a discussion for a different day, okay? So the idea is that if, well, let's not write it this way, the distribution of, we write it this way, n minus 1 times, or sorry, yeah, no, that's right, n minus 1 times, I lost my train of thought, s squared over sigma squared is chi-squared of n minus 1. Okay. Where your s squared is 1 over n minus 1, sum from I equals 1 to n of x minus x by minus x bar squared.
So remember how we calculated the variance before? You do the expected value of the deviations from the mean that you're given, right? The mean of the distribution is x by minus mu squared, right? Notice in this case, we're not doing the variance of the distribution. We're trying to estimate the variance of the distribution using the sample mean. So this is what's referred to as the sample variance.
And again, if you've done any statistics, you've probably calculated the the sample variance by dividing by n minus 1 rather than dividing by an n. The reason why is because you're trying to estimate things. And again, this is a discussion for next semester if you're taking stats. Okay. All right. Sample variance. But generally speaking, if you estimate a population parameter using your random sample, you lose what's referred to as a degree of freedom. Okay? So in this case, when we're summing 16 things together, you lose a degree of freedom when I use the sample variance to estimate. Okay? I still want to do the same thing. I will still divide everything by the variance of the distribution that we have. And it's written this way then. But since we're using that rather than the 50, this is chi-square of 15 now rather than 16. It's one less. Okay. Now notice that is n minus 1 times s squared over sigma squared. We divide it by the sigma squared. The n minus 1 piece would cancel off with that 1 over n minus 1 in front. So again, if we pop back over to our chi-squared table and now look at, there it goes, and now look at 15 rather than 16, there's your 25 and there's your 7.261. So again, you get 0.9. It's the same idea. The big deal is, for this particular one, and I know I've emphasized it a couple of times now, but the big deal is that if you replace the known mean of the distribution with the mean of the sample, you lose a degree of freedom. So since we're adding 16 of these things together, it's chi-squared of 15 when we're done. You just lose 1 in this case, yeah. All right. Let's do one more here. All right. So looking at part A, is part A any different than the normal distribution types of problems we've done before? No. Okay. So part B asks you if x bar is the mean and s squared is the variance from a random sample, determine x bar. The probability that x bar is less than or equal to 150.9. Now again, they tell us specifically that, pardon me, They tell us specifically that the normal distribution here is given to us, right? They tell us that the mean is 147 and the variance is 12.3 squared, right? So to convert this over to a problem that we've done before, it's already in the less than or equal to form. What would we subtract from the 150.9? Good. Because again, when we do the sample mean, the mean of the sample means doesn't change, right? What do we divide by? Good. Square root of the variance squared divided by the sample size, right? That's where the 12.3 over 5 comes from. Okay. Literally, that's the only thing that we're doing new, isn't it? Dividing the variance by the n. The n in this case is 25. Otherwise, this is not a new problem, right? The last part's a little new, but the idea here again is to create a chi-squared distribution, right? Okay. Let's not worry about the 0.9. Not worried about the 0.9 at all right this second. Okay. Let's create a chi-squared distribution in the middle. Okay. So remember again, your s squared by definition is this. Right? That's our definition of our sample variance. Sum of the deviations squared divided by n minus 1. Okay. And n minus 1 s squared over sigma squared is chi squared of n minus 1. Okay. All right. Now I want to create a chi squared in the middle. I want to create a chi squared in the middle. To change s squared into a chi squared, what do I need to multiply by and what do I need to divide by? Need to multiply by n minus 1 and divide by sigma squared, right? In this case, what's n minus 1? 24. Variance is 12.3 squared. Right? How many degrees of freedom? 24. Yeah, good. N minus 1. Okay. So looking this direction, I would need to multiply by 24 and divide by 12.3 squared. I'm just going to give it a different letter, so I don't feel like rewriting it. Doesn't matter. That's what it would look like, right? If I multiplied through by 24 and divided by 12.3 squared. But in particular, it's chi squared of 24. That's the distribution it has. So going back over to our chi squared distribution table, maybe, there it is. Looking up at the top row, what's the only combination of columns I can use to get a 0.9 when I'm done? If I have two constants, one on either side. What is the only combination? Actually, technically there's two combinations I could use. Tell me one. Yeah, I could use a 0.95 and a 0.05. I could have also used that one and that one, right? That would give me that gives me 0.95. Never mind, I lied. We just want 0.9. There is only one. Okay. Only the one, that's the columns, right? What row do you think we want to look at? 24. So I would need this 13.85 and 36.42. Now, can I remember those two numbers? So going back over here, you want 24a over 12.3 squared to be 13.85. That's the lower number that we would want. 24b over 12.3 squared is 30, what did it say, 6.42? Is that what I said? I think it load. Oh, I did remember it right. 36.42. And then you can solve for your A and B at that point. The numbers aren't important in this problem. The entire idea was what do I need to do to the problem? What do I need to do to the sample variance to change it into a chi-squared? That's the whole point of the problem. You have to multiply it by n minus 1 and divide it by the variance. Okay? All right. We'll do more of this next time. This, like I said, this stuff won't be on the test. So your test will be, it starts at the normal distribution, right? Starts at the normal distribution. Started talking about transformations of random variables. So we had doing that CDF technique to find new PDFs from given PDFs and doing a transformation of the variable, doing the inverse function, right? And then we've done basically sums and constant multiples of independent distributions, right? That was kind of what we've done, right? I'll get review problems posted this afternoon, so you have those. I'll be around pretty late this afternoon, too, if you've got questions about things. And, of course, I'll be around Monday as well. So, anyway, have a good one. See you all later.